Ladies and gentlemen, let's continue with our module in heat and mass transfer. I specifically refer to the textbook of Cengel and Ghajar, the 5th edition, and we are busy with chapter 6. Chapter 6 is on the fundamentals of convection. We are going over this material very quickly because most of it you've already done in fluid mechanics. So we're just connecting the heat transfer and the fluid mechanics with each other because that is actually what convection heat transfer is. This chapter consists out of 11 parts, so it is quite a long chapter, and we have made progress until paragraph 6.8, solutions of convection equations for a flat plate. And previously I've showed to you the derivation of the boundary layer thickness, which can be written or approximated as approximately 4.91 divided by the square root of the Reynolds number, and that is specifically for laminar flow over a flat plate. That's from the fluid mechanics part. We wanted to do the same with the heat transfer. And again, I'm going to show you there are lots of similarities between the fluid mechanics and the heat transfer, but the most important result that actually came from the previous work is that the boundary layer thickness divided by the thermal boundary layer thickness is always approximately Prandtl number to the third. So after all this theory, let's just do a practical example so that you at least can see what we are doing, where we are going, and to get a practical feeling for what we are busy with. So the example that we are going to do is flow over a flat plate. Flow over a flat plate, and it's flow of air, and its temperature is 20 degrees Celsius. Its free stream velocity is equal to 1 meters per second. The Prandtl number is equal to 0.7309. The density is equal to 1 kilograms per cubic meters. And the viscosity is equal to 1 multiplied by 10 to the minus 5 kilograms meters per second. So here's the flat plate, and this boundary layer is going to develop there. And we would like to know where x is equal to 500 millimeters from the leading edge, and where x is equal to 1 meter from the leading edge, what will the boundary layer thickness be for the fluid flow? And let's use blue for that, as we have done with the previous lecture. So that is for the velocity boundary layer there in blue. And we also would like to know it for the thermal boundary layer. Now, one of the most important things that we've mentioned previously is that if the Prandtl number is equal to 1, then these two lines will be exactly on top of each other. This is 0.73, so it's not exactly that, but its order of magnitude is approximately the same. We will come back to the thermal boundary layer just now. So the question is to determine the boundary layer thickness for the fluid flow, the velocity boundary layer, as well as for the temperature gradient for the heat transfer. So let's look at typically at x equal to 0.5 meters. So at x equal to 0.5 meters, we can go and calculate the Reynolds x. Reynolds x means where x is 500 millimeters from the leading edge. So the Reynolds number is equal to rho v. Normally we would write diameter. In this case, it is the characteristic length, which is now the length of the plate, or the length where we actually want this, divided by the viscosity. So you can write it like that, or you can write it as rho Vx divided by the viscosity, just as you want. So the x indicates the Reynolds number based on the length, x, from x equals 0. So for this case, the density is equal to 1. The velocity is also equal to 1. and the distance x is 0.5 meters from the leading edge. The viscosity is equal to 1 multiplied by 10 to the minus 5, and that will give us a Reynolds number of 50,000. Okay, now at this stage, you wouldn't really know if this would mean that the flow is laminar or turbulent. We're going to do that in the next section, but you'll see that it is actually laminar flow. So it's laminar flow, and that is then the Reynolds number at x equal to 500 millimeters from the leading edge. Let's look at where x would equal to 1 meters. At x equal 1, it would be 2 times that, isn't it? But you can write it out. So the Reynolds number would also be 1 multiplied by 1. X is now 1 meters divided by 1 multiplied by 10 to the minus 5. And that would now be equal to 100,000. And again, it is actually on the edge of between laminar and turbulent flow, but for the purpose of this chapter, let's assume the flow is laminar for both cases. So, if we want to get the boundary layer thickness, there's the equation for it. So it is equal to 4.91 multiplied by x divided by the Reynolds number based on x. So that is at x. My apologies, I forgot here to include x there. So it's 4.91 multiplied by x. So the boundary layer thickness where x is equal to 0.5 would then be equal to 4.91 multiplied by 0.5 divided by the Reynolds number, the square root of it, which is 50,000. Okay. And that is going to give us a boundary layer thickness of 10.9 millimeters. So 10.9 millimeters, 1 meter from the leading edge, just so that you've got a feeling for a boundary layer thickness. Right, so now we can go and do exactly the same for x equal 1 meter. So for x equal 1 meter, I'm sure I do not have to do the calculation for you, so it's 4.91. X is now just equal to 1, divided by the square root of the Reynolds number, and if you go and do it, it would be equal to 15.53 millimeters. Okay. So if we do it here in the sketch, then that distance is 10.9, and that one is 15.53 millimeters. Let's go and calculate now the thermal boundary layer thickness. For the thermal boundary layer thickness, delta divided by the thermal boundary layer thickness is approximately equal to Prandtl to the third. It is not exactly, but it is very close to it. So at x equal to 0.5, we've got delta divided by the boundary layer thickness is equal to Prandtl to the third. The boundary layer thickness is equal to 0.0109 divided by what we want. The thermal boundary layer thickness is equal to, and the Prandtl number is equal to 0.7309 to the third. The only unknown is the thermal boundary layer thickness, where x is equal to 0.5, and that is equal to 12.19 millimeters. Okay, we can go and do exactly the same for x equal 1 meters from the leading edge. Again, delta divided by that is equal to Prandtl to the third. The boundary layer thickness in this case is equal to 0.01553 divided by the thermal boundary layer thickness is equal to the Prandtl number, 0.7309 to the third, and from that we can solve that the thermal boundary layer thickness is 17.24 millimeters. Okay. Did you all follow that? It's very simple, but it gives you a practical feeling now for what is happening. So coming back to our boundary layers, we can see that in this case, because the Prandtl number is smaller than that one, the thermal boundary layer is thicker, and this distance is 12.19. 12.19, and that distance there is equal to 17.24. What does it mean, those boundary layers? It would mean that if we look at the velocity boundary layer, okay, it would mean at that distance that the velocity from that point onwards will all be equal to the free stream velocity, which is 1 meters per second. Okay. And from there on down, it would be 99%, that would be 99% of 1 meters per second. The thermal boundary layer is the temperature gradient, temperature difference between the free stream and that one, and it means that if we want to, I'm going to clean it up a little bit here for myself. Something like that. That would be the free stream temperature, and from there on, if the plate is cooling, it's at a lower temperature, the temperature would decrease. Something like that. Do you all follow it? Good. Now we're going to go through the theory again very quickly. Lots of equations. I'm just going to highlight some of the most important ones to you. Specifically paragraph 6.9, it's already there on the screen, the non-dimensionalized convection equations and similarity. So again, what we do is we look at the continuity equation, the momentum equation, and the energy equation, and we non-dimensionalized everything. So x is equal to, x star is equal to x divided by L. Okay. Y star is equal to y divided by L, etc. The pressure is equal to the pressure divided by rho v squared, and the temperature, the non-dimensionalized temperature, is equal to T minus Ts divided by T infinite minus Ts. The result is, if we write those three equations down in a non-dimensionalized format, you can sort of see that they look almost the same, except for one or two differences. Do you see them? Okay. Now what is important from that is that you can actually now show that two of the most important parameters in that equation that again follow is the Reynolds number, which we can write like that: velocity multiplied by the length divided by the kinematic viscosity. If you don't like that format, you can write it as rho VL divided by the normal viscosity, like that. And the other one is the Prandtl number. Prandtl number we can write like the viscosity divided by the thermal diffusivity, or we can write it as Cp multiplied by μ divided by K. And those two parameters tells us that if we use that there's similarity between fluid flow and heat transfer. Thus, if you would do an experiment, let's suppose in a wind tunnel, of the wing section of an aeroplane, and that is equal to the velocity you typically use air, and that would be the length of your aerofoil. Obviously, you will do it at a certain viscosity of the air, a Prandtl number of the air, the Cp of the air, etc. Most of that can be written as, can be taken up by the Prandtl number. Okay. Now, so if you do these experiments in a wind tunnel, and this model of yours are similar to maybe the aerofoil of an Airbus. Okay. So this is maybe 200-300 millimeters. That is what, I don't know, 3-4 meters in length. And again, air is being used, but a different velocity V2, and the Prandtl number conditions are totally different. But my sketch isn't that good. If you would look at any specific position X, on the scale, then that distance and that distance will be exactly the same. So they will be geometrically similar. If they are geometrically similar, it means that if we calculate this Reynolds number and that Reynolds number, and they are the same, then the results would be similar. And you know that from fluid mechanics. It therefore means that we can do experiments in the wind tunnel, and we can take drag measurements. Now let's suppose this Reynolds number is equal to 1 million. Then we can use these results for the case where that Reynolds number is also equal to 1 million. However, the length might be totally something different length. Let's suppose in this case L2, and that is equal to L1. So L2 can be much larger than L1. As long as we keep the Reynolds numbers the same, we have similarity. And also, of course, which is more challenging, is of course keeping the Prandtl numbers the same. If we also can keep the Prandtl numbers the same, then the heat transfer will also be similar. So there is similarity between the fluid mechanics and the heat transfer. What it does is actually it would take 6 variables, which would be the length, the velocity, T infinite, surface temperature, kinematic viscosity, and alpha. And in these 2 terms, there are actually many more terms, but in general we have 6 variables here. And we can reduce them by doing experiments only with 2 variables. So, well, if we want to get all the properties for this aerofoil, we have to do experiments for 6 different variables. If we go to the wind tunnel and we keep this the same, and we do experiments only at different Reynolds and Prandtl numbers, we can get exactly the same results. So it can save us a lot of time and money. So paragraph 6.10 is specifically then on the functional forms of the friction and convection coefficients. And what it does is also making use of this non-dimensionalized study is to go further. And what they do is to indicate that the friction coefficient X at a specific point is one or other function of X, so the distance from the leading edge, and the Reynolds number. So the drag is only a function of X and the Reynolds number. So if we want to know exactly the drag at that point there and that point there, if the Reynolds numbers are exactly the same, then the friction coefficients will also be exactly the same. It would obviously mean that we can do that all around the aerofoil and at the end do an integration to get the average friction coefficient, but we will get to it just now. So that is the first functional form that is derived. The other one is for the Nusselt number. Now the Nusselt number is a new variable to you. Remember, it is the non-dimensionalized heat transfer coefficient. We're still going to use it a lot, so be patient. So, and that is a function also of x, the Reynolds number, but then also the Prandtl number. So, if we do the integration of these two equations, then we can determine that the average friction factor is only a function of the Reynolds number. Okay. And to indicate that this is the average, I'm going to show it like that. Okay. This is the average. So if you do the integration at different points x all around the profile, you can get the average or the total skin friction coefficient, and from that you can get the average. And then the same with the Nusselt number. The Nusselt number is going to be a function of the Reynolds number and the Prandtl number, and actually the Grashof number, but we will get to the Grashof number a little bit later, so you can just ignore that in the meantime. Means it's a function of the Reynolds number and the Prandtl number, and again the Reynolds number based on one or other dimension, L. And this is very important to us, that functional form of the equation. So in paragraph 6.11, he discusses the analogy or the analogies between momentum and heat transfer. So it summarizes many of the very important concepts that we've done up to now. It shows that if you are interested in forced convection, forced convection means there's flow and there's heat transfer simultaneously. If you do that, then there are two things that you are normally interested in. The first one is to get the friction coefficient, or the average one. And the second one is to get the Nusselt number, or again, the average Nusselt number. This gives us the shear stress on the wall, and that is important to us because that shear stress determines the thrust of the turbines for the airbus, or for flow over a plate or through a heat exchanger. It's either the fan or the pump. So it is always something that you pay for. It costs you money. This one, the shear stress. Then the other one is the Nusselt number, and that gives us the heat transfer rate. And then it shows a very, very elegant solution for those equations that I've showed to you by using the special case of a Prandtl number equal to 1. So if we just go back to our equations also, we can see that if Prandtl number is equal to 1, it means that these two boundary layer thicknesses are going to be exactly the same. An order of magnitude, that's typically what happens with air. The Prandtl number is 0.7, but order of magnitude is 1. Okay. So typically for this special case of Prandtl equal to 1, it derives that the friction coefficient as a function of x divided by 2 is equal to the Stanton number, which is equal to the Nusselt number divided by the Reynolds number and the Prandtl number. I don't know if you all can see it down there. Let me see if I can show it to you on a PowerPoint. There you go. So the friction coefficient divided by 2, forget about the Stanton number for a moment. The friction coefficient divided by 2 is equal to the Nusselt number divided by the Reynolds number and the Prandtl number. Okay, so ST is called the Stanton number. Stanton number. Okay. Now it's just another equation. But there's something very special in this equation, and it shows to us how special nature is. It shows us that if you know the drag characteristics, you actually also know the heat transfer characteristics. Okay, so think about what I'm saying. I'm saying that if you know the drag characteristics, you can actually determine the heat transfer characteristics. It means that if you do an experiment in a wind tunnel to determine the drag on a flat plate, and all you measure is velocities and the drag on the plate, you can get the friction coefficient, CF, and when you have that, you can actually determine the Nusselt number from it, and then you know what the heat transfer characteristics will be. So that's a very special thing written by these equations. Now it is true that all gases or fluids do not have a Prandtl number of equal to 1, and for that other derivations were done by other people. All the details are not showed in your textbook, but for those cases, before I get to that, no, sorry, that's right. So for other Prandtl numbers, so for other Prandtl numbers, it can be shown that for a flat plate, that the CFX value is equal to 0.664 multiplied by Reynolds X to the minus a half, and the Nusselt number at a specific point X, that same point, is equal to 0.332 multiplied by Prandtl to the third multiplied by Reynolds X to the half. So for a flat plate, here's the Reynolds number and the Reynolds number. So for that Reynolds number, you can determine it by multiplying it by 0.664 multiplied by the square root of the Reynolds number. Here it is almost the same. Here you can see that one is a half. Okay, and this is equation 6.82 in your textbook. Okay. Now, as I've mentioned, for other Prandtl numbers, this was done by Chilton and Colburn, and it is called the modified Reynolds analogy. Okay, so the modified Reynolds analogy. The modified Reynolds analogy is valid for Prandtl numbers larger than 0.6 and smaller than 60. So most of your gases and liquids will actually fall into this category for the modified Reynolds analogy. Take note, the assumptions here is a flat plate and laminar flow. Okay. And then it can be derived that CFX divided by 2 is equal to the Stanton X Prandtl to the 2/3. And this term on the right-hand side is also called the J factor. J factor with the H showing for heat transfer. Thus, what this analogy tells us is that if you take the friction coefficient divided by 2, you actually have the J factor. You've got the heat transfer characteristics. Okay, J is equal to Stanton, Prandtl to the third. Stanton you can write as Nusselt divided by Reynolds Prandtl. So that is the one format in which you can write it, or you can also write it as CFX multiplied by Reynolds L divided by 2 is equal to Nusselt X Prandtl to the minus third. Okay. Those are the two formats given in your textbook. So for a flat plate and laminar flow. Now let's do an example. And do not only now think of this example as just lots of formulas that we have to push into the formulas to calculate the values. The example would be typically of a flat plate. Okay. A flat plate with dimensions of 3 meters and 2 meters in those directions. That's 2 there. And this flat plate is hanging on a rope, and here we've got a scale that can measure the drag force on it. Okay? And as it is hanging there in still air, we would put the scale on 0. We will 0 it because there is no drag force on it, except now for its own weight. Then we put on a fan here, so that we have over the flat plate a velocity of 7 meters per second. And okay, the temperature we can go and measure is 20 degrees Celsius. Why would we like the temperature? Because the viscosity is a function of temperature. The density also a little bit function of temperature. So at that temperature, in table A15, we can go and get the properties. And the properties for air is a density of 1.204 kilograms per cubic meters, a CP value of 1.007 kilojoules per kilogram Kelvin, a Prandtl number of 0.7309, a viscosity of 1.802 multiplied by 10 to the minus 3, and a K value of 0.02514. I think many of you will not be able to read it. Just be patient, I'm going to read it to you just now. I'm going to repeat it to you just now. So the temperature of the air is 20 degrees Celsius. The CP value, the density is equal to 1.204. The CP is 1.007 kilojoules per kilogram Kelvin. The Prandtl number is 0.7309. The viscosity is 1.802 multiplied by 10 to the minus 3. And the K value is equal to 0.02514. Everybody, anybody who missed one of them, can't read it, they should repeat? Not? Okay, great. So, okay. And after we've put on this fan, we can then measure there on the scale that the force is equal to 0.86 newtons. Okay. So the difference would be 0.86 newtons. So that would be the drag on the flat plate. So the drag force is equal to the average skin friction coefficient multiplied by the surface area multiplied by rho v squared divided by 2. The measured force is equal to 0.86, is equal to the friction coefficient, that is what we want to determine now, multiplied by the surface area of the plate is 2 multiplied by 3. You all agree? Yes, good. We also have to take into consideration the backside of the plate. The air flows on both sides of the plate, not only on one. Okay. So it is both sides of the plate, then multiplied by the density, which is equal to 1.204, multiplied by the velocity, which is 7 squared, divided by 2. So from this we can get the friction coefficient. And the friction coefficient is equal to 0.00243. Okay, so that is, let's call it the fluid mechanics part of this problem. You can go and do this experiment. This modified Reynolds analogy tells us that if you've got the friction coefficient, you can get the heat transfer characteristics without taking one measurement. except now obviously getting the properties of the air at 20 degrees Celsius. But you're not going to measure the heat transfer rate or the surface temperatures or anything else, or the outlet temperature. So let me show you how we're going to do that. So the Reynolds analogy says that Cfx divided by 2 is equal to the Stanton Prandtl to the third. Okay. Because we have the average Cf value, we can write that as the average Cf and the average Stanton and the average Prandtl number also. So the Cf value is equal to 0.00243 divided by 2 is equal to the Stanton number multiplied by the Prandtl number is 0.7309 to the 2/3, from which we can solve that the Stanton number is equal to 0.001497. The Stanton number, again, is equal to the Nusselt number divided by the Reynolds number and the Prandtl number. Thus, we want to get the Nusselt number, we've got the Prandtl number, we just have to calculate what was the Reynolds number. So let's calculate the Reynolds number. So that is our unknown for now. So our Reynolds number we can write as rho VL divided by the viscosity of the plate, of the air. The density of the air is equal to 1.204. The velocity of the air over the plate is 7. The length of the plate is 3 meters over which it flows. It flows in this direction. Okay, so we want that characteristic length. Divided by the viscosity is 1.802 multiplied by 10 to the minus 3, and it gives us a Reynolds number of 1.403 multiplied by 10 to the 6. Very close to turbulent flow, but let's assume in the meantime this is still laminar flow. So, coming back to this equation now, we can write that the Stanton number is equal to the Nusselt number divided by the Reynolds number, Prandtl number. The Stanton number we have determined as 0.001497 is equal to the Nusselt number, that is what we want to determine, divided by the Reynolds number, which is equal to 1.403 multiplied by 10 to the 6, divided by the Prandtl number 0.7309, and the result is that the Nusselt number is equal to 1,536. If we have the Nusselt number, then we can calculate the heat transfer coefficient. The heat transfer coefficient, the Nusselt number is equal to the heat transfer coefficient multiplied by the characteristic length divided by K, K of the fluid. Nusselt number is equal to 1536, is equal to the heat transfer coefficient multiplied by the length, which is 3 meters, divided by the thermal conductivity, 0.02514, and from that we can get that the heat transfer coefficient will be equal to 12.87 watts per square meter degree Celsius. Thus, this analogy tells us that if we do fluid mechanics experiments, we get the friction factor, then we can get the Nusselt numbers. Or we could have done heat transfer tests to determine the drag coefficient, the other way around. So let's suppose the temperature of the surface is 30 degrees Celsius. We want to do the opposite now. So we put a heating element here inside the plate, we heat the plate to 30 degrees Celsius. Then the heat transfer rate is going to be the heat transfer coefficient multiplied by the surface area multiplied by the temperature difference, Ts minus T infinite. The heat transfer coefficient is equal to 12.87. The surface area, again, both sides of the plate. So not only 2 by 3 meters, 2 by 3 multiplied by 2 equal to the surface temperature is 30 minus the free-stream temperature is 20, and then we can determine the heat transfer rate is equal to 1,554 watts. Do not get confused between the heat transfer rate and the heat flux. In many cases, we are going to refer to both. So the heat flux is equal to the heat transfer rate divided by the surface area. The heat transfer rate is 1,554 watts divided by 2 multiplied by 3 multiplied by 2, because in this case the heat transfer will be to both sides of the plate, not only to one side, and that will give us a flux of 128.7 watts per square meter. Thus, this analogy tells us something very special. If we therefore consider a flat plate, then you can do two types of experiments to get the same result. You can do the experiment on the fluid mechanics part with the velocity there and measuring the drag force on the plate. Or you can do the same experiment by putting an electrical element in the plate, measuring the surface temperature. So that would be the heat that we put into the plate, which in this case would be 1,554 watts, 1,554 watts. That's the surface temperature. That is temperature of the environment. If we have done this experiment, only the heat transfer experiments, it would have been possible for us to get the force on the plate. Do you understand what the analogy means? It's something very special in nature. Analogy between fluid mechanics and heat transfer. Ladies and gentlemen, any questions on this problem? Thanks, Cameron.